If you put two computers side by side and both of them say 64 gigabytes of memory, you might assume they can run roughly the same size AI models. But with local AI, that can be completely wrong. A Mac with 64 GB of unified memory may be able to load and run a surprisingly large language model on the GPU, while a Windows PC with 64 GB of system RAM and, say, a 12 GB or 16 GB graphics card can hit a wall much earlier. And at first, that sounds strange. 64 gigabytes is 64 gigabytes, right? Not really. The important question is not just how much memory the computer has. It's where that memory is, which processor can access it, and how fast the data can move. That's what I want to explain today, because this is one of the most misunderstood parts of local AI hardware. Let's start with a normal Windows desktop. Imagine I have a PC with 64 gigabytes of DDR5 RAM and an NVIDIA graphics card with 6 gigabytes of VRAM. On paper, the system has 80 gigabytes of total memory. That sounds even better than a 64 GB Mac. But the problem is that those two memory pools are separate. The 64 GB of DDR5 is system memory. The CPU uses it directly. The 6 GB of VRAM is attached to the GPU. The GPU uses that directly. And for AI inference, that distinction matters a lot. If I want the GPU to run a model at full speed, ideally the model weights need to fit inside VRAM. So if I have a model that requires 24 GB or 30 GB just for the weights, my 60 GB GPU can't hold the whole thing. Yes, I still have 64 GB of regular RAM, but that does not magically turn into 64 GB of VRAM. That's the part that causes so much confusion. People look at Task Manager, see 64 GB of system memory, and think, why can't my GPU just use all of that? Technically, it can access some data in system memory, but the performance characteristics are completely different. The GPU's own VRAM is sitting right next to the GPU and is designed to provide enormous bandwidth. System RAM is connected through a completely different path. And with a discrete graphics card, moving data between system memory and the GPU often means crossing PCI Express. That connection is much slower than the GPU talking to its own VRAM. So if part of my large language model is in VRAM and another part is in regular RAM, I can still run the model using CPU or GPU offloading. But now I've introduced a bottleneck. The model may work. It just might not work very quickly. This is why you'll often hear people say something like, I can run a 70B model on my 24 GB GPU. What they often mean is that part of the model is on the GPU and the rest is sitting in system RAM. That's completely valid, but it is very different from fitting the entire model inside fast GPU accessible memory. Now let's look at Apple Silicon. On a Mac with Apple Silicon, the memory architecture is different. Instead of having one large pool of system RAM and a completely separate pool of dedicated VRAM, Apple uses what it calls unified memory. The CPU and GPU share the same physical memory pool. So if the Mac has 64 GB of unified memory, the GPU can potentially access a very large portion of that same 64 GB. That's the key difference. It does not mean the Mac has 64 GB of traditional dedicated VRAM, but from the perspective of running a large AI model, the GPU has access to far more memory than a Windows machine with a 60 GB discrete graphics card. And that is why a 64 GB Mac can sometimes load a model that simply does not fit entirely on a 60 GB or 24 GB PC GPU. Let's use a simple example. Imagine I have a quantized large language model that needs around 40 GB for its weights. On my Windows PC with a 16 GB GPU, there is no way that 40 GB model is going completely into VRAM. I have to split it. Maybe 60 GB goes onto the GPU. The rest goes into system RAM. Now the CPU and GPU may have to work together, or data may have to move across the PCIe connection. On a 64 GB Apple Silicon Mac, that same model can potentially live inside the unified memory pool that the GPU can directly work with. There is no traditional copy the model from 64 GB system RAM into a tiny separate VRAM pool problem. That is a huge advantage when your main limitation is model size. This is why people running local AI often talk about high memory Macs almost like they have giant GPUs. You'll see someone running a 70B model on a Mac with 64 GB or 28 GB of unified memory, and then someone with a powerful Windows gaming PC asks, why can't I do the same thing? I have 64 GB of RAM too. The answer is that the memory is not arranged the same way. But there's an important warning here. Unified memory does not mean unlimited performance. Just because the model fits does not mean it runs as fast as it would on a high-end NVIDIA GPU. This is where memory bandwidth becomes extremely important. Imagine memory as a giant storage tank. Capacity tells me how much water the tank can hold. Bandwidth tells me how wide the pipe is. A 64 GB unified memory system may have a very large tank, but how quickly the GPU can move data through that memory still depends on the specific Apple chip, and large language model inference is often heavily dependent on memory bandwidth. During token generation, the hardware has to repeatedly read enormous amounts of model weight data. So if I have a 40 GB model, the system is effectively moving a huge amount of data through memory over and over again. That's why two Macs that both had 64 GB of memory can still produce very different AI performance. One chip might have much more memory bandwidth. It might have more GPU cores. It might have better overall compute. So I never look at 64 GB unified memory and assume I already know how fast the machine will be. Capacity tells me whether the model may fit. It does not tell me tokens per second. This same idea applies to Windows systems too. A desktop with 64 GB of DDR5 memory can have plenty of capacity, but system memory bandwidth is still nowhere close to what a high-end GPU can achieve with GDDR memory. Modern discrete GPUs can have enormous VRAM bandwidth. That is one of the reasons they are so fast at LLM inference when the model fits completely in VRAM. And this creates a really interesting trade-off between Macs and Windows PCs. A Windows machine with an RTX class GPU may have much faster raw inference performance on models that fit entirely into VRAM. But once the model becomes larger than the available VRAM, things get more complicated. The Windows system may have to start offloading to RAM. Performance drops. Meanwhile, the Mac may have enough unified memory to keep that larger model in one shared high bandwidth pool, so the Mac can sometimes run the larger model more gracefully. That doesn't automatically make the Mac faster. It means the Mac has a different advantage: capacity accessible to the GPU. This is why I think the phrase 64 GB of RAM is almost useless when comparing AI machines. I need to know what kind of memory it is. I need to know whether the GPU can directly access it. I need to know the bandwidth. I need to know how much dedicated VRAM the Windows GPU has. And I need to know the model I'm actually trying to run. If I'm running a 7B or 14B model, this whole discussion may not matter very much. Those models can fit easily on many GPUs. In that case, an NVIDIA card may deliver extremely strong performance. But if I'm trying to run a 40 GB, 50 GB, or even larger quantized model, memory architecture suddenly becomes one of the most important parts of the machine. There's another reason unified memory helps. It can reduce unnecessary copying. In a traditional CPU plus discrete GPU system, data may exist in system memory and then need to be copied into VRAM before the GPU can process it efficiently. That takes time and uses bandwidth. In a unified memory architecture, the CPU and GPU are working from the same physical memory pool. They can access the same data without needing the exact same kind of duplication between separate memory systems. For workloads involving large datasets, models, images, or shared processing between CPU and GPU, that can be extremely useful. But again, I want to be careful here. Unified memory is not magic. The CPU and GPU still compete for memory bandwidth. The operating system still needs memory. Your applications still need memory. If I buy a Mac with 64 GB, I should not assume all 64 GB is available for model weights. macOS needs some. The inference framework needs some. The KV cache needs some. Other applications need some. So maybe I can use a large percentage of that memory for AI, but never the entire advertised number. This matters especially with long context windows. Let's say I load a large model and it takes 45 GB. I still have memory left. Then I start using 32K, 64K, or 28K context. Now the KV cache grows. Memory usage increases. And suddenly a model that loaded perfectly might start putting pressure on the system. It's exactly the same basic problem you see on GPUs. The weights are not the only thing consuming memory. That's why I always recommend some headroom. If the model file itself is already almost equal to your total available memory, that is probably not going to be a comfortable setup. Another important difference is software. On Windows, NVIDIA has a huge advantage because the AI ecosystem has been built around CUDA for years. A lot of inference frameworks are highly optimized for NVIDIA hardware. TensorRT, CUDA kernels, flash attention implementations, specialized quantization runtimes, there's a huge amount of software built around that ecosystem. That can make NVIDIA GPUs extremely fast. On Apple Silicon, local AI often relies on metal-based runtimes, llama.cpp, MLX, and other Apple-specific optimization paths. These have improved a lot, but software support still matters. A model that runs beautifully on an NVIDIA GPU may not perform exactly the same way on Apple Silicon, and the reverse can also happen with certain workloads. So I wouldn't reduce this comparison to Mac good, Windows bad, or NVIDIA good, Mac bad. They're optimized around different strengths. A high-end Windows PC with a big NVIDIA GPU gives me incredible compute performance, mature AI software support, and often very high token generation speeds. A high-memory Apple Silicon Mac gives me access to a much larger GPU usable memory pool and a compact system. For local LLMs, that can be extremely valuable. Think about a system with 64GB of unified memory versus a Windows PC with 64GB of RAM and an RTX GPU with 12GB of VRAM. If my model needs 10GB, the Windows machine may absolutely fly. Everything fits on the GPU. No problem. If my model needs 20GB, now the 12GB GPU can't fit it entirely. The Mac might be able to keep the whole model inside unified memory. If the model needs 40GB, the difference becomes even more obvious. The Windows PC still has enough total RAM to load it, but now it's relying heavily on system memory and offloading. The Mac has a much larger memory pool directly available to its GPU. So the larger the model becomes, the more important this architectural difference becomes. And this also explains why some people build multi-GPU Windows machines. If I install two GPUs with 24GB of VRAM each, I can potentially split a large model across both cards. Now I have much more high-speed GPU memory. With enough GPUs, a Windows workstation can absolutely outperform a Mac on huge models. But now we're talking about more power consumption, more heat, more hardware, more cost, and more setup complexity. The advantage of unified memory is that Apple gives you one large memory pool without requiring multiple discrete GPUs. That simplicity is one of the reasons it became so popular among people experimenting with large local models. There's also an interesting mistake people make when comparing prices. They look at a Mac with 64GB unified memory and compare it to a PC with 64GB RAM. But for AI, the better comparison may be against the amount of VRAM required to run the same model. And large amounts of dedicated GPU VRAM are expensive. Consumer NVIDIA GPUs usually offer much less VRAM than high-end workstation or data center cards. So if your goal is specifically to load very large local models, unified memory can offer a different kind of value. But if your priority is maximum speed on models that fit in 24GB or less, a powerful NVIDIA GPU can be extremely difficult to beat. That's the trade-off I think people should understand. Mac gives you memory flexibility. NVIDIA gives you raw GPU performance and ecosystem strength. And the best choice depends on the size of the model. For smaller models, I care a lot about GPU compute and software optimization. For huge models, I start caring much more about how much memory the accelerator can actually access. That's why I never ask, does this computer have 64GB of memory? X place. I ask, how much of that memory can the GPU actually use efficiently? That one question changes the entire comparison, because 64GB unified memory on an Apple Silicon Mac and 64GB DDR5 RAM on a Windows PC are not equivalent resources. On Windows, your 64GB system RAM mainly expands how much data your CPU can hold and gives you space for model offloading. Your GPU is still largely limited by its dedicated VRAM if you want maximum performance. On the Mac, that same 64GB pool is shared between the CPU and GPU, so a much larger portion of it can be used directly for GPU-accelerated model inference. That is why the Mac can sometimes run surprisingly large models. It's not because Apple somehow created 64GB of magical VRAM. It's because the architecture removes the hard wall between normal RAM and GPU memory. And for local AI, that wall matters a lot. So the next time you see someone running a huge model on a 64GB Mac, and you look at your Windows PC with 64GB of RAM, wondering why the experience is completely different, now you know. The number is the same. The architecture is not. And when you're running large AI models, architecture can matter just as much as capacity.